And welcome back, fellow night owls. This is Dr. Nighttime, continuing with our going through the written answer questions to the fall 2020 LTAM exam. And this is number 4. So it begins, Dan and Mark are each age 50 and have independent future lifetimes. They purchase a fully discrete last survival whole life insurance of $100,000. You are given that mortality for each life follows the standard ultimate life table. Interest is 5%. Premiums of G per year are payable until the second death. Premiums are payable semi-annually for the first 20 years, then annually thereafter. G is calculated using the equivalence principle. Commissions are 10% of each premium. Other acquisition expenses payable at issue are 70% of G. And use the two-term Woolhouse formula for the single and joint life annuities to evaluate stuff when it's more than annual. All right. So, part A, show that the probability that exactly one of Dana and Mark survives 20 years is 0.14 to the nearest 0.01. You should calculate the probability to the nearest 0.0001. All right, that's not too bad. You look in the tables. You look in the tables. This is for joint lives. This is for single lives. Notice I've got the 50, 60, and 70-year ages underlined. Those will all be relevant. It's a little obvious why we'll need 50 and 70. 60 will become a little obvious later. So, you look in the tables, you get probability of a 50-year-old surviving 20 years. You take 2 times that probability times 1 minus that probability. You get 0.1405, right? Simple enough, right? There are 2 ways one could survive. Either Dana could survive and Mark doesn't, or Mark survives and Dana doesn't. Okay. Hi, Dr. Nighttime again. Quick interjection here. A lot of you are probably looking at this first line I have up here and saying, wait a minute, that's not the value I have in the table. And yeah, it's not. Not only that, this doesn't get you 0.1405. It's because this is the value for 60 years, which I end up using later. The value for 70 years is 91,082.4. Yeah, so hopefully that clears that up. My apologies for the mistake. Now back to the continuation of the video. This is where it starts to get a little more difficult, and the main difficulty becomes in knowing how to cut and shuffle and juggle all of the formulas and values involving joint lives, last survivorship probabilities, and all of that. So we need to find a double dot compounded semi-annually of last survivor of 250s, angle 20. To do that, first we're going to want to do it assuming that we're only measuring stuff annually. And we would look in the table for this, but the table doesn't have the last survivor stuff. So we have to use the principle that for any last survivor quantity, it's twice the corresponding single life quantity minus the corresponding joint life quantity. Right? This comes from assuming that if one of them is paying a premium of 1 and the other is also paying a premium of 1, you could either view that as whoever dies first plus whoever dies second, or just you plus you, right? Either one is going to work, right? It should be noted that formula is true whether or not the lives are independent of each other. However, it is not true if you have reason to believe that purely because suppose that Dana and Mark were married. There actually is reason to believe that simply by being married, you're likely to live a little longer. Specifically, To put it bluntly, it's really tough to get a date when you're in a wheelchair. You know that disability discrimination is not something to be taken lightly, but it happens. The other, and I guess also issue that shouldn't necessarily be taken lightly is it's possible that just because you're living with someone, if you fall and hurt yourself, you're more likely to have somebody be able to call an ambulance, or even just yet another issue that shouldn't be taken lightly, but if you're living with someone, you're much less likely to develop certain unpleasant mental conditions like depression and such. So with all that unpleasant stuff out of the way, short version is, I don't think I've ever seen an LTAM question that presumed that just by being married, you were likely to live longer, but that's exactly the sort of thing they could ask, and they haven't asked it yet, so it's ripe for them to pull one of those now, so they could say, 1 point on some question. Why would it be a good idea to presume that just because you're married, you're likely to live longer? And you'd have to name one or two of those reasons. So worth getting that out of the way now. This problem doesn't deal with it, but a future problem might. Anyway, so this formula is true whether the lives are independent of each other or not. And one last really annoying bit, we can find the probability, we can find the actuarial present value of an annuity for a 50-year-old with a 20-year term, but not for two 50-year-olds with a 20-year term. No, that table has a column for 10-year terms, but nothing for 20-year terms. Meh. So we have to do more juggling and say, all right, we'll subtract the one for the 10-year term, and then for the next 10 years. And how do you do the next 10 years? Well, by that point, if you die, then you die, and it doesn't matter. But if you don't die, then you're both 60 years old, and then you have another 10-year term after that. So you have to multiply by the endowment factor. And I don't think there's a column. Let me double check. I don't think there's a column. No, there's no endowment column here. So you have to calculate the endowment figure directly. 10-year discount times the probability of surviving. This should be 10, not 20. My apologies. Surviving 10 years twice. I had it at 10 in my notes here, so what comes after is correct. Anyway, so you crunch all those numbers, algebra happens, lots of algebra happens, and you finally get that this figure is 13.0764. Now we use the Woolhouse formula and say, well, this is being compounded twice a year, not once a year. Okay, so if you remember from problem 1, I drew a little diagram like this. I won't go through the time to explain all the algebra and what everything represents there, of like snipping away the triangles. As promised, when I'm done with these 6 problems, I will upload a video that goes into that more thoroughly so that you can understand more about why I'm drawing something like this. But long story short, even though the special case they give you on the formula sheet is for looking infinitely far into the future, so they don't have this endowment for however long, right? Because if you go infinitely far into the future, that endowment value is going to be 0, so you'd be subtracting 0 anyway. Here, we do need to subtract that out. Again, we need to crunch the numbers on that. And we crunch all those numbers, and we get 12.9201. Okay. So we're done with parts A and B. For part C, show that the gross premium G is 850 rounded to the nearest 10. You should calculate the value to the nearest 0.1. So we get our formula. There's the 70% initial expense loading, right? So 0.7G gets subtracted out. You only keep 90% of any given premium because of the expenses of 10% that they talked about way back at the beginning here. Commissions are 10% of each premium. For the first 20 years, it's compounded semi-annually. Everything after that, you have to wait 20 years, hence the 20-year deferral, compounded annually, and that equals 100,000 times big A of 50:50 bar. Well, of course, the table doesn't give you 50:50 bar, so you have to do that whole thing again where you say 2A50 minus A 50:50, right? Imagine, if you will, that if you paid each of them $100,000 on death, you could either view that as 100,000 to Mark and 100,000 to Diane, or 100,000 to whoever dies first, 100,000 to whoever dies second. Either way, they've got to add up to the same thing. So you get this formula out of it. Fine. And then for the deferred annuity here, again, it's just you do that same trick again to calculate a last survivor figure when you only have the single life and the joint life. Crunch the numbers again. Of course, you need endowment of 50:50 for 20 years again, but we already know how to calculate that. So doing everything we've already done before, more algebra happens. We get that this figure is 5.15324. We already calculated this one to be 12.9201. This figure here we calculate to be, well, multiplied by 100,000, so you get 13,193. More algebra happens, and you get G equals 847.55, which does round to 850. All right, that's half the points on the problem. And I feel like the points after this are actually easier to get, or at least less algebra. So, show that the reserve at time 20, if both lives are alive, is 22,400 to the nearest 100. You should calculate the value to the nearest 1. All right. So it makes the most sense to my mind to value everything prospectively. So however much you have in the bank already at 20 years in, plus 90% of the premiums that you keep afterward, that's going to be A double dot 70:70 bar, has to equal 100,000 A 70:70 bar. Of course, we need yet another, we need to use the same old trick to evaluate a 70:70 bar. And then we could either do the same trick for A double dot 70:70 bar, or we could just say A double dot 70:70 bar equals 1 minus big A 70:70 bar over D. Hopefully you've seen that formula to death and have it committed to memory by accident by now. But just in case you haven't, after I'm done with the Woolhouse formula video, I'll have another formula explaining where that one comes from. It's a simple little sum of a geometric series trick. I owe you guys that explanation once we're done with everything else here. So you do all the algebra, and you get that the policy value after 20 years is 22,439. Then for the reserve at time 20, if only one of the lives is alive, that's actually much, much simpler. If only one life is alive, then you don't care about the dead person anymore. The dead person isn't contributing anymore. You can view it like it's essentially a life insurance policy on just the one person. So it's just policy value at time 20 plus 0.9 G A double dot 70 equals 100,000 big A 70. You can look both these up in the table. Finally, numbers you can just look up from the tables. You get big V equal, or V at 20 equals 33,658. All right. One last part. Calculate the reserve at time 19.5 if both Dana and Mark are alive at that time. Assume a constant force of mortality between ages of 69 and 70 for the individual lives. So we would set up this formula, the amount that you have in the bank at time 19.5 plus 0.9, and there's a mistake. This should be 0.9 G over 2. So you have V at 19.5 plus 0.9 G over 2, right? Because you obviously don't pay the premium, the full premium both halves of the year. You only pay half the premium each half of the year. Times 1.05 to the 1/2 equals this probability that both are alive times the corresponding policy value at time 20 plus probability that both are dead. If both are dead, then that means you have to pay out the 100,000. And plus 1 minus probability both are alive minus probability 1 is alive. So check that. 1 minus probability both are alive minus probability both are dead. There we go. That's probability that 1 is alive times the policy value for 1 being alive. Q69 is 0.009294. So P69.5 for 0.5, it's going to be 1 minus square root. We do square root, not linear interpolation, because it said constant force of mortality rather than uniform distribution of deaths. So we calculate that. We get 0.004658. Probability that both are dead. Sorry, no, so probability that both are alive is 1 minus this square, which you'll notice it's just going to be 1 minus Q69. Because with constant force of mortality, saying you have to survive both halves of the year is the same as saying, same probability as saying both have to survive 1/2 of the year. So you could just say 1 minus this quantity is going to get you this one that we need here. Probability that both are dead is just probability that 1 is dead times itself. And then you plug those into here, and you get the probability at, you get the policy value at 19.5. This figure is incorrect, and I'm going to have to re-record some of this. Pardon me a moment while I get the correct value. Yeah, so I corrected the mistake. Policy value is 21,620. Sorry for the mistake earlier. And as always, if you like the way I explain things and want to arrange private lessons, click the link in the description. And until next time, this is Dr. Nighttime wishing you a good night.